So dot product of our vectors is the only form of multiplication of vectors that we have. All of the properties that we've talked about so far, none of them had to do with multiplying two vectors together. That's because the dot product of two vectors is the only type of actual multiplication we have, but it's a little bit different than just multiplying the two vectors together. So I wanted to show you there's vector u is u1, u2, and vector v is v1, v2. So there's the x component for each and the y component for each. To take the dot product, it would look like this, where you'd have u dot with v. Then this is not u multiplied by v, this is a dot product. So it's u dotted with v. That's exactly how they say it, and that's how it should be kind of interpreted. But this is going to be where I take u1, times it by v1, add it to u2 times v2. Now the thing that people forget is they'll forget to do the addition. They'll take the x's and multiply them together. They'll take the y's and multiply them together, but they will forget to add them together. So a rule for vectors with dot product is that the dot product always gives a scalar, never a vector. So the dot product is always going to give you a scalar. A scalar is just a constant, so it's just going to give you a number. You should never be left with a vector, and if you're left with a vector, you did something wrong. So that's something to kind of remember. So let's look at some examples of, just for really quickly, I have a few that I want to go over, but let's look at some examples of dot product. So let's say my first vector is 4, 5, dotted with 2, 3. And this is one way to write our vectors. So the first one would be u and the second one would be v, or whatever. It doesn't really matter. But to take the dot product of these two vectors, I have to multiply the x components together. So that would be 4 times 2. And then I add it to that multiplication of the y components. So in this case, 5 times 3. Sorry about that. So 4 times 2 is 8, and 5 times 3 is 15. So add these together, and my final answer should be 23. Can you tell that I did this at school? I apologize for the bell. So the next example is 2, -1. So we're going to do a few of these. They're going to be super short and super sweet. But 2, -1, and dotted with 1, 2. So go ahead and try that really quickly. Multiply the x's, multiply the y's, and then add those numbers together. So if I do that, I have 2 times 1 plus -1 times 2. So it's the x, 2 times 1, x here, and then plus -1 times 2. Also make sure you don't multiply them together in like x and y. You don't want to multiply x's and y's together. You want to multiply the x times the x of the second and the y times the y of the second. In this case, you should get 0, and that would be your final answer. And last one, 0, 3, dotted with 4, -2. Go ahead and pause and try that one real quick. But if I do this, I would take 0, which is x, times 4, plus 3, which is y, times -2. I don't know why I keep doing that with this. I apologize. So 0 times 4, plus 3 times -2. Add those together, and I get -6. So those are my dot products. That's how dot product is worked. There are some properties of dot products that I want to talk about. So I'm going to give it 2 seconds, and I will have the properties up on the screen. Okay, so here are some properties. Go ahead and pause and write them down. But these properties are really important. Some of them are pretty self-explanatory, like the first two should make the most sense to you, that if I have u dotted with v, it's the same thing as v dotted with u. So it doesn't matter which order they go in, it just, this process is still the same. 0 vector, remember that's the 0 vector, dotted with a vector should give you 0, which would make sense because the 0 vector is 0, 0, so 0 times anything is 0. But the two that I really want to focus on, and actually the last three are the most important, but the two that I really like to focus on is 3 and 5. If I have u dotted with v plus w, it's the same thing as kind of distributing and taking u dotted with v and u dotted with w. So if you ever get something like this, you can add the vectors together first before you take the dot product, or you can take the dot product first with each vector and then add those results together. Forrest talks about how if I have v dotted with itself, it's the same thing as the magnitude squared. So if you wanted to find the magnitude and you only had vectors, and you could do dot product as well, but really this one's not as important because you should know how to find the magnitude by now. So it's not really the best way to do magnitude, so I wouldn't really worry about it too much. But this last one is C. So if I have C, which remember C is a constant. So if I have a constant times two vectors, the important thing here is that I'm not multiplying the constant and distributing. I'm only multiplying it to one of the vectors. So notice that I can either multiply that constant to u first and then dot product it with v, or I can multiply that constant to v first and then dot product it with u. Or I can take the dot product and then multiply the cn at the end. So these two right here, the third and the fifth one, I would say are the most important to kind of pay attention to. But that's really up to you. So yeah, I would definitely focus on those. I do have a couple of more examples of using properties of vectors, so let's go on to another example really quickly. Okay, so here's our next example. I want to do two parts to this just to kind of give you kind of an idea of how properties would work. But we're going to work with three different vectors. We're going to work with u, v, and w. So our first one states that we want to find u dotted with v and then timesing it by w. Notice there's not a dot product here. So this would be multiplying the vector by the dot product of the vectors by the actual vector itself. My suggestion would be to do this first. We take u and dot it with v. So if we do that, remember that u starts with -1, multiply that to 2 for v. Then I'm going to take plus 3 times -4. If I do this, I get -14. So that -14 is now going to be multiplied to vector w. So that's going to be -14 times whatever vector I have left, which is -1, -2, 1 and -2, and then I can distribute those in. So my final result in this is actually a vector. Now, -14, 28, when I multiply by -14, this is a vector. But the dot product still gave us a scalar. So the dot product has to give you a scalar, but if you're using it in another step, then it is okay to end with a vector. So that's going to give me a vector. And that's the answer to part A. Part B says to take u, dot it with 2 times v. Now remember that 2 can either be multiplied at the end, or it could be multiplied to do things the way that they are presented to me, but that's just me. It really doesn't matter. You can do whatever feels comfortable to you. So I have -1, 3 is u, and I'm going to dot it with 2 times 2, -4. So when I do this, I'm going to multiply in that 2 first before I take the dot product. So I have -1, 3, we're not changing that. Dot with 4, -8. Now I want to take the dot product. And that's going to be -1 times 4 plus 3 times -8. X times x plus y times y. And in this case, I have -28, which is a scalar. And that is it for my examples for dot product. So go ahead and sign on to my math lab and finish those assignments.